How's it going, you guys? So a lot of you probably think of me as someone who talks about Lisp a lot. It's probably one of the biggest things I've talked about on my channel in the past year. And it's been a big thing that has been near and dear to my heart, but I like to kind of look around and see what else is out there. Now, something that I noticed is that surprisingly, for someone who pretty much exclusively for a lot of my videos talks about Lisp, substantial amount of you guys are not searching for Lisp. If you look at my actual YouTube statistics, you will notice an equivalent amount, or at least a relatively similar amount of you guys that are looking for Lisp are also looking for Rust programming, which is really weird, kind of strange. I don't know if it's actually the same ratio, because if it is the same ratio, then that means that even more people are searching for Rust than Common Lisp. And so when I saw that, probably the first thing that came to mind is why? But the other thing was also, maybe I should do some content to intrigue you guys. Now, I could take this as an opportunity to talk about Rust, but obviously Rust has more than enough publicity, and I'm not really interested in making things purely for the sake of attention. So instead, I wanted to take this opportunity to pull some of those views towards a project that really deserves it and has been on my radar for a long time. That is the programming language Carp. Carp is a great programming language that combines a lot of the great things that you see in Lisp and a lot of the great things that you see in Rust, puts them together and makes a Lispy, beautiful language that we'll be talking about today. Now, before we get too far into today's video, I wanted to give a big shout out to today's sponsor, Skillshare. Skillshare is an online learning community with thousands of online classes and members across 150 countries. For me, Skillshare has filled a pretty large gap that I've found building up over the years in computer science that I found couldn't really be filled with YouTube, blogs, or even the general online documentation for a lot of frameworks. I find that for the technical side, a lot of that stuff is easy to find, but finding curated, clear, and effective knowledge on graphical design, productivity and time management, CSS, and a lot of the more creative, inspired parts of computer science, kind of difficult. Skillshare, on the other hand, is a collection of great resources on topics like this. Every course is broken up into chapters, which makes it easier to start watching and come back later, or skip ahead to the parts that you really feel like you need to see. Recently, I took a look at the class Real Productivity, How to Build Habits That Last with Tom Frank, and I was really invested in the idea of using habits to manage my life, which is really what a lot of the class is about. While these goals may sound small, these goals really build up, and it helps to kind of think of small individual things that we can start working on. Skillshare offers individual classes that are short and can be finished in less than an hour in some cases. Once again, thanks to Skillshare for sponsoring this video. If any of what I've talked about interests you guys, be sure to check out the link in the description below, where the first 1,000 of you to click this link will get a free 1-month trial with Skillshare. So first of all, what actually is Carp? Well, Carp is a Lisp first and foremost. If you look at the syntax, you'll see just how Lispy it can be. In fact, its core syntax is mostly derived from Clojure. However, unlike Clojure, it is statically typed, compiles to C, can produce a standalone executable without any dependencies, so it doesn't have a runtime, and it also doesn't have garbage collection. As a result, instead of having garbage collection and instead of dealing with raw pointers, while you can do that, instead you would use the borrow checker. It's very similar to how Rust does this, and as a result, you can write very Lispy code and not really have to worry too much about the pointers and having to clean up. Instead, a lot of this is handled for you just by passing around this sort of ownership, and we'll talk about that later on in this video. Now, you're probably thinking, a statically typed Lisp, what does that really matter? Well, a statically typed Lisp has a lot of benefits. The biggest reason to this is the idea of static checking on a macro is kind of difficult. A lot of languages, for example, Nim, has issues with this as well, and a lot of other languages kind of have to work around their type system to make this work. Probably the most common way to do this is to have dynamic or untyped macros, and basically having something like symbols like you would see in most other Lisps as a way to sort of handle this. Then you have basically two runtimes. You have your macro runtime and your normal runtime that your actual program will be running with. Unfortunately, this means that you don't have sort of the eval features that you would expect, but obviously with a language that compiles to a executable and doesn't really have an interpreter in the same sort of idea that you would in a lot of those other languages, and no runtime, obviously packaging eval would be very expensive and a huge pain to really work with. So you obviously don't want that. And so this is kind of how Carp does it as well. So the way that they do it is you have basically a dynamic runtime, which is what's happening at compile time and when you're working from the REPL. And then you have a normal runtime where you can actually execute things. But as a result, you don't have those dynamic features. Now, while the approach to the actual runtime is very similar to a lot of these languages, since Carp is a Lisp, and I'll kind of show the syntax to you in just a minute, you will actually notice that the actual way of using macros is a lot more simple. For example, Nim, like I mentioned before, is a very macro-heavy language, but since it doesn't have a S-expression-based syntax, macros become very difficult to deal with because you don't have just one single parentheses-based call syntax. You now have to deal with infix, and a lot of different operators to keep in your head. And so this is kind of where Carp comes to stand out and really stand into its own sort of field, is where it has this sort of dynamic runtime, as well as having the S expression based syntax. Now, outside of macros, what else can you count on? Well, that's pretty simple. Probably the first thing would be the ownership system similar to Rust that I mentioned before. This kind of takes away the garbage collection and the worries of sig faults, for example, so you don't have to worry about the garbage collection that you get in Common Lisp, and you don't have to worry about those sig faults that you get in writing C code. This is a huge benefit in a lot of cases because when you're working with Common Lisp, you run into limitations in performance when it comes to real-time applications, as I mentioned here. And a big thing here is that it is possible, but it really depends on the application. Because if you want to write real-time applications, you do have to really consider this when it comes to garbage collection, as well as considering consing. You don't want to be consing too much because you're going to basically be increasing that memory consumption. And it makes applying this to something like an embedded system really difficult. And moving on to actually selling the Lispers on static typing, don't worry, I'm not expecting you to think that you always need to have static types, but there are times where it's helpful and there are benefits to it. For example, and this isn't all static types, this is specifically models similar to the one seen in Carp. The actual type system helps you a lot of the way. For example, there's no exceptions anymore, so it's actually kind of simplified for you, and you no longer have that worry in the back of your head that you're going to be throwing an exception, as well as removing those pesky nil errors that you get a lot that can be so difficult to find when working with class and multi-methods. So this can really simplify that problem, as well as making discoverability easier. Documentation is substantially less necessary since you have the entire type signature to rely on. You have typed holes, which we'll show off later, which kind of allow you to sort of dig into the code and be able to determine what needs to go where, as well as making your code more concise. You have polymorphism. Polymorphism, especially parametric polymorphism, is substantially easier, and it's been an issue in Common Lisp to actually get something like that while not having to make it super verbose. That hasn't really been easy, and it hasn't really been solved yet, unfortunately. But there is attempts to fix it. It's just not there yet. Prevents edge cases, so you don't have to really deal with all these extra checks that you have to do. A lot of the times, these are just solved by restricting the type signature. And then finally, you run into refactoring. Is just substantially easier. You can make it easier in dynamic types, but it's just so much easier to just do it with static types because you, especially in a good, like a decent dynamically typed language, you can get pretty far. But with a good type system and a statically typed language, it's just really hard to beat when it comes to refactoring. In a language like Java or C with a pretty poor type system, it doesn't really matter. Dynamic types are pretty similar in the amount of safety that you get. So in those cases, it's not a big deal. But in languages like Carp, you actually get a noticeable improvement when it comes to refactoring and these other things that I mentioned before. Now, that's enough talking. Let's get into a quick demo, dig into each of these different things, and kind of give you a quick example of how to get started and all that sort of stuff in Carp. Let's get into it. All right, so first of all, let's just go into how you guys can actually install it. The easiest way is to simply go to the latest release, download the zip, and you can unzip it and you'll get a directory like this. Now, what you're going to want to do is you're going to want to export this directory. So wherever you end up storing this guy, I have this under my home directory under Carp, and then this file, this directory right here is where it is. If I go to an actual project where I have this, you're going to want to actually export this directory as well as directory/bin in your path. And then this way you will have quick access to Carp as well as its standard library available to you. I did this with dirinv. which is basically a program that lets you manage environment variables, but you can just throw this in your bash RC and access it that way. All right, so now that you have gone ahead and exported those variables, so now if I go ahead and just do my path, you'll see that Carp is at the top. And then if I echo my Carp directory, you'll see that it is where that other directory was. So now if I just do Carp and run the command, I will get a REPL. Let's just give that a second. And there we go. So we now have a pretty simple REPL. And so just to get the little help, you can do help. And you'll get a bunch of little shortcuts and information. So you can get information on the compiler, the language, the core API, Gitter, which is basically their community, and you can kind of ask questions there. You get shortcuts and the about. So first of all, let's go ahead and actually load a project. So the easiest way to do that is just go ahead and do load and then give it the path to a file. So if I just look at my files, you'll see down here that I have tmp.carp available. And run that. And then now I have loaded my project and I can do build. To build it, that'll just take a little bit. Obviously, there's a little bit of code in there. I built an executable. And then I could type run. Or as I mentioned over here, I have some shorthands. So I could type run or I could do X, and this is a shorthand for run. And there we go, it's ran it. And so as you can see, it's just kind of printing some random stuff. This is using a file that I was kind of using to just prepare for this video. If I like updated the file and I wanted to reload it, I could just do R to reload. Now I've gone ahead and opened up the project next to this. Obviously, I'm not going to really be going too deep into this, so I'm just going to go ahead and build it. And I'm not going to really dig too much into the code. I'm going to try and keep this as surface level as possible while still helping you guys understand the language. So probably the first thing is just a simple add function. Now our main actually contains nothing. So when you execute a file, it will run the main function. But we still get the sort of REPL interface that you would expect. So let's go ahead and just insert that. So now let's do add 1 and 2. And there we go. And we get 3. So this is kind of what you would normally be expecting, as you would expect. And the actual functions are pretty straightforward. For those of you guys that aren't used to Clojure, it uses sort of angle brackets like this every once in a while. It has a few special syntax stuff, but basically it's just extra stuff to make things a slight bit more readable. What I was going to say is that you can define functions like that. You can also just define variables. So def x equals 1, and then x, there we go, and we get a 1. As you can tell, since it has to like compile this stuff behind the scenes, it can be a bit slow at the REPL. But a lot of the times when you're just kind of working and debugging, you're not really dealing with this sort of runtime issue. Since a lot of the times you're mostly just fixing a little compiler issue, because most of the pains that you run into are during compile time rather than having to fix them all at runtime. All right, so now you know how to define functions and variables. So let's go ahead and show you kind of what you can do from the REPL just in general before we dig a bit deeper into the language. So like I said before, you could do help to kind of get some information. You can do help shortcuts to kind of get a bit of these shorthands that can kind of be helpful when you're working from the REPL. And then if you want to kind of just see everything that's out there, you can do env. Now this is going to list every single function, every single variable that's been defined. It will show you basically everything, which can be really helpful when you're starting to learn the language, just to kind of see everything that's out there. And if we just kind of like move around and we scroll up, you'll even see that there are modules. There's a bunch of different functions that have been defined for each of them. Now we can actually take advantage of this ourselves, and we can do quite a lot with them. So if we wanted to kind of investigate one of these modules, for example, probably the most common module that you work with is array. As you can see, it has all these different functions that are defined. Probably the most simple one to work with would be empty. So what that'll do, let's go ahead and do :I array. And to kind of access one of these functions, we'll use a dot. We'll do empty ? And then we will get the information. So it says where it's defined. It gives us the actual type signature, and it gives us some documentation, checks whether an array A is empty. Now, the really cool thing about this is this type signature, which might seem a little bit foreign, but you can kind of think of it this way. This is how kind of a lambda is written, and it'll kind of simplify things a bit. So a lambda is fn, the arguments, so A plus, so let's add A to 1. And then we get a Clojure. So we can go ahead and do that. And there we go. So we've added some numbers together. So fn is how you create a lambda, basically. And so as you can see, we do fn, the arguments, and its return. Now the function signature kind of follows this same sort of format. So empty, or array.empty question mark, has a type signature of fn, meaning it's a function. And it takes the arguments of a reference to an array of A, and we'll ignore this B for now, and it returns a bool. So a bool is like a Boolean. That kind of makes sense. If we wanted to kind of access this, then probably the first thing we'd want to do is we would do array.empty question mark, and this is how we call it. And then we have to give it an array. Now arrays out of the box have a nice reader macro where you can do 1, 2, 3, and then we can go ahead and call that. Now we get an error. It says that we cannot match this type of array int to reference array r2, making this function call that we just did. Now the reason for this is that, as we see, it takes a reference to an array of A. So array A is just a generic, so array A will actually be array int in this case. So all we have to do is resolve this reference issue. Now, all we have to do to make this a reference is we can use the reference function, which is just ref, and run that. And then it will take a little bit to run and so is array empty false. Now, obviously this is a little verbose having to type that, so we can shorten this up by just using the and symbol here, run that. But once it's done, we will get the same results. So this is basically a reader macro for those of you that are from the Lisp background. You're kind of pretty used to seeing these every once in a while. So this is a quick way to make a reference. So how does this whole reference thing work? Well, basically what we're doing when we're giving a reference is we are giving permission for a function to actually access this value. Since for those of you guys that are coming from C, by default, you would be passing by value. In most languages, and as well as Carp and Rust, you pass by reference. And so for this reason, you need to actually give permission to access the reference that to a variable. And so that's basically what we're doing here. Giving reference means that we are giving permission to access this variable. And this is kind of the way that we can kind of make sure things aren't being used in multiple places at once. And this is kind of how the type checker and borrow checker, I'm not too sure what they actually call it in the Carp compiler, but that sort of idea gives you a way to kind of avoid, say for example, in two places, one place you are reading a value and another place you're freeing it. You can run into an issue where you're accessing a null pointer, which is obviously bad. And so this is kind of a way to get the compiler to be able to figure that out for you, as well as a way to tell the compiler, I want to allow this function to access it. I'll hopefully cover this again in the future. Obviously, this is just way too surface level, and I'd like to dig more into it myself as well. All right, so now let's kind of break down what that just one was from earlier. Just one was an abstract data type known as a maybe. So that might have sounded very confusing, but let's just go ahead and break this down. So we have a maybe. So this is a module, and we have just. So maybe just one. When we run that, we get a just one. If we do the type of maybe nothing, then we will get a maybe A. And if we do the type of a maybe just one, we will get a maybe int. So what exactly are we looking at here? Well, both of these guys actually have the type of maybe. And in some languages, you may be used to hearing the term some type. Basically, it's a type that can have a bunch of different states. And it's really powerful because it allows us to do what I was saying before, where you remove the need for exceptions. So let's go ahead and just quickly dig into how this works. So like I showed before, you could do just one, and we will get a just one. And right here, I've made some example code, a function that will take the first element. And when it takes the first element, it returns a maybe. Now that maybe can be a just and then the value that it got, or it could be nothing. And in most cases, when you try to do something like this, you would get an exception, but instead we're getting this nothing back. Now, as a result, if we go ahead and run this, we will get just one. Because basically what's happening here is we're taking the first element, that is a 1. We're taking a reference to that, we're turning it into a string, and then we are printing it. So there we go. So now we're able to kind of print the element that we are receiving. Now, how can we actually go from this just one and turn that into a actually usable value? Now there's a bunch of different ways you can do this. So up here, I've actually written a type signature, and we can go ahead and compile this, run it when it is an empty list, and we will get a nothing, because when we did first on an empty list, there's nothing to pull out of that list. I keep saying list, but I mean array. I keep pulling out the first element and there's nothing there. So in normal cases, in a lot of languages, we'd throw an exception. We don't have that option, so we return a nothing. Now we have this type signature up here. If we went ahead and compiled this, just give this a second, we will still get a nothing. Compile, we get a just one. Now how can we turn this into an actual value? The best way to do that is to use pattern matching. So we can use a function called match. It actually might be implemented as a macro. I'm not too sure on that one, but the way that it works is very simple. So instead of doing this right here, what we will do is we will take our value and we will go ahead and take this guy and we will match on it. So we have two different states that it could be in. It could be a just X or it could be nothing. And so this is what we're going to do to actually use it. So if it's just an X, then we will print that X. If it is nothing, then we will print, oh no. And so now if we compile this, just give it a little second, we will get a 1 because that was what we were able to retrieve. Now if there was nothing there, we compile it, we get an oh no. Now if we wanted to say maybe restrict this and say we don't actually want to be passing back a maybe, say we wanted to restrict it to pass back an int, then we could set a type signature. Now, if we try to compile this, we will get a type error. It will say cannot match type int against maybe D. Now, the way to actually restrict this and actually do this properly would be to actually move this guy up here, and then right here, and just X. And then our fallback will be 0. So this is kind of how we'll handle the error case. We should be able to get the types to work out. There we go. And so now our function will just return an int and we can restrict that. And we could do a lot more stuff. Say, for example, maybe we wanted to restrict things more and we wanted to say maybe here we wanted to restrict it. We could do the int, and this will add an additional strictness to it, ensuring that what we're getting back is an int. So now instead, if I just did this returns an A, even though it's more generic, we're going to always be getting back an int. So say, for example, if this contained hello, if it contained a string, and I try to compile it, I would get a type error because it does not match the constraints that we have given it. The is basically the equivalent to kind of restricting one value locally, and then sig is a way to give a type signature to, say, a function or a global variable. All right, guys, so that's a pretty simple run through of the language. I'm going to quickly just go through some of the things that I would like to see from the language in the future. And maybe if you guys are interested in hacking on it, it's written in Haskell. So you guys can go ahead and take a look at the code base and maybe try and contribute. I'm going to be trying to do this since I'm learning Haskell on the side for this year. It's kind of my 2023 sort of resolution is to try and learn Haskell, which is part of the reason that I played a bit more attention and understood this language a bit better than I used to. So the first thing is I wanted to be able to actually mark mutability. Right now, mutability is not really enforced very heavily, which I would like to have is a way to kind of tell what is mutable, what is immutable. That would be good to see. A possible implementation of the unsafe, of an unsafe macro, kind of like how Rust has an unsafe block. It would be cool to have that. Since you can have pointers in this language, since obviously this compiles to C and there's a lot of ways to kind of write C bindings just in Carp. I didn't get to dig into that. It would be cool to talk about that in the future. Another thing I'd like to see is actual type classes or traits. I say coming soon, but there's only really been talk, so I'm not too sure if it's actually coming soon. There's an actual pull request investigating this. Exposing bindings and completion in more of a user space way would be nice to see. Proper multi-threading support would be great to see. Better macro facilities. Right now, I've seen quite a lot of bugs and issues with it. Just general polishing in general, as well as reader macros would be awesome to spot. Generally, I would just like to see more all-around polish. But there's a lot of potential here, and I think there's a lot of good that can come from Carp in both the Lisp ecosystem as well as just general programming. There isn't really a lot of attempts like this, and I think it has a lot of potential to really bring Lisp into the modern day and achieve things that not a lot of people have done with it. And that's it for today's video, guys. I really appreciate all you guys watching and sticking through to the end. Just a few things I wanted to mention. If you wanted to learn more, there's documentation. There's the Gitter server where you can ask questions, as well as a bunch of documentation that I'll try and link down below for those of you guys that are interested. Sorry, it's been hard to record a lot of these videos. Been kind of sick recently. Hopefully you guys, that didn't stand out too much during the video. My voice is kind of gone from all the coughing. But yeah, I appreciate it. Once again, I wanted to give a big shout out to all my supporters on Patreon, as well as my supporters on GitHub sponsors. It means so much to me to have you guys supporting me. And one final thank you to Skillshare for sponsoring this video. Thanks everyone for watching, and I'll see you next time.